Let's try to record, and we're recording. Thank you, thank you, thank you, you rich people at Zoom. Can you imagine how rich Zoom is right now? Look at their profits over the last 3 quarters. Woo! Makes you think, why couldn't you think of that, right? What a time to be alive. Okay, so if we look at number 6. Here's how I wanted you to interpret number 6. If I can speak properly. So here's how I wanted you to interpret 6. Now, I'm not saying if you didn't do it this way, you're wrong. I'm not going to like take points off of you. This is the learning part now. No matter what you did on this problem or will do, hopefully this is the learning part. So first off, first. And this is what's different than the problems we've done before. It's not so to describe or draw the sample space. So the first thing I want you guys to understand is that with this particular problem, it ain't like flipping a coin 2 times or 3 times or 4 times. It's not like rolling a pair of dice. If you try to write out the sample space here, you're going to need a lot of space. I mean, think about this, and I don't want to get too far ahead of what we're doing, but think about for the first card, how many options are there? Give you a hint, it's a number between 51 and 53. You got 52 options. And that means for the second card, you have 51 options. And for the third card, you have 50 options. Now, I ain't a calculator, but I know if I multiply 52 times 51 times 50, that's a big old number. That means I got lots of different scenarios. I ain't possibly going to write that out, can I? Should I? Right? So we got to understand, and I've alluded to this before, and that's part of the reason we wrote that scary stuff down last class with those axioms of probability. We have to understand that drawing out the sample space for most experiments is impossible. And so what we have to do is we have to reason what's a better way to think about this experiment. Another way to interpret what I'm saying is how we know how to calculate probability is a very sort of direct way. We know that the only way that we can compute probabilities right now is we can count the number of events, and then we divide it by the total number in the sample space. That means in order for us to compute probabilities, at least if we assume only what we talked about in class, we got to be able to count every scenario where, for example, you get 3 black cards. Does that make sense? Now, of course, we know that that's inefficient, and we also hopefully realize if that's the way we had to do it, we would never get anywhere in life. So what we need to realize is there's got to be a better way, and how do we do that using our rules of probability? So the second thing that I was hoping you would realize we need better counting methods than just our definition of probability. So I'm just going to write it down in shorthand. Remember, the probability of an event was the number in that event divided by the number in the sample space. I mean, it's really hard to imagine we could use this definition to answer this problem, right? I mean, I'm not saying you couldn't. You could definitely do it, but it doesn't seem like it's the best way. Does anybody have a question or a comment? So in many ways, you could think of this problem as like a foreshadowing problem. The purpose of this problem is for you to get stuck and then hopefully realize, I got to learn something new. Now, of course, you could torture yourself. You could have went and got all this paper and laid it on the floor and said, all right, I'm going to write out let me write out all the scenarios where I get a black card on the first. And then, you know, you could do that, I guess. Theoretically, it would just take you a long, long time, and you'd probably mess up along the way. So does anybody have a question or a comment? Okay, now, let's think of it from a different perspective then. Perhaps we should sort of, I always use this analogy or metaphor, I don't know what the correct English word is, but when I look at this can from this angle, I see like a can. It looks like a cylinder, right? To me, at least. Now, if I go put it way over there and I look far away, from far away, you might argue, well, it looks like a rectangle. Now, you're going to say, it's not a rectangle. Okay, so imagine if you shined light on it, what would its reflection be in the board? It would be a rectangle. Does that maybe make sense? And then, of course, if I went the opposite way and like I set it on the ground, or if I looked at it from top down from far away, it's going to look like a circle. Think shadows. We call those projections. So this can be interpreted in a few ways if I sort of imagine different perspectives. Just like if I take a cone and I look at a cone from far away, it might look like a triangle to me. But then if I look at a cone from the top down, it might look like a circle. So what I'd like you to do is always, when you're problem solving, is sometimes you need to step back from a problem and ask yourself, is there a better perspective to look at this problem? And you're going to say, well, what does that have to do with your can thing? Well, it has everything to do with it. The way humans quantify size of something like this is, what is the size of an object like this? We call it its volume. And how do we, what is a natural way to quantify that? And also, it turns out to be probably the most, not just sort of intuitive way, but it's also the way that makes sense when we do it in advanced math, is to say, okay, let's look at a cross section of this thing. And if we look at a horizontal cross section, if I cut it in half, its cross-sectional area is a circle. And so then I can think of this can as being made up of lots and lots of circles kind of put together. The same way, if you've ever looked at a ream of paper, has anybody ever seen it? Or even a book, look at the side of a book. You could think of that as like a block is really being made up of all these very thin rectangles sort of stacked on top of each other. Now, of course, that might just confuse you right now, I'm not sure, but again, it's just a different way of imagining certain things. Okay, nonetheless, here's how I want to imagine this problem. I know I can't really write out all the scenarios. That might take a while. So the first sort of question says, what is the probability I get all black cards? So if we understand about a deck of cards, there's hearts are red, a standard deck. Diamonds are red. Spades and clubs are black. And so the thing is, if I pick a first card, I might, what's that?
Another question is the jokers in the deck too?
Well, if I say standard deck, no jokers, right? So sort of that's what I was alluding to in the beginning. Unless I otherwise tell you, just assume that a deck is standard. Yeah, but you're correct. If you add jokers, then you're clearly going to change the odds. Okay, so here's one way to think about it. So pick one card. What does our intuition tell us? So our intuition and the basic law of probability, or classical probability, I should say. I don't want to say basic. So what do they say? They suggest the probability of a black card is, well, half the cards are red and the other half are black. So we would imagine what? Well, there's 13 and 13, 26. So we would imagine 26 over 52, which is 1/2. Or if you'd like, you can write that as 50%. Now, the reason I'm writing this number as 26 over 52 or 1/2 or 50% is every one of us might think of that differently. You know, you might say I have a 50-50 chance of getting black, or I might say I have 1/2 chance because half are black, half are red. Or maybe the math person in you says, well, there's 26 black cards and there's 52 total, so it's 26 over 52. Luckily, all three of those numbers are the same, right? They're all the same. Okay, so what we would have maybe want to do then is, if we're going to pick 3 cards without replacing, maybe instead of thinking of this as an experiment, we think of this experiment as having 3 stages to it. So now we repeat. Now here's what we have to really think outside of the line. There are 2 scenarios now. There's a scenario where I pulled a black guy first, or there's a scenario where I pulled the red guy first. Do you understand that? So there's 2 scenarios. So case 1 is black card first. Case 2 is the red card came. Do we understand this? So now we have multiple scenarios. So one way that we can sort of visualize these stages is we can do what's called draw a diagram or a tree. So one of the common ways of doing this is to sort of break down this experiment into stages. So again, this is not necessarily what you have to do, but this perhaps might be something you want to do. So let me elaborate on that. You might say, okay, I got the first card I pulled was a black card. So now there's 2 scenarios. At the next stage, I can get black again, or I can get red. Does that make sense? And then similarly with case 2, I can get red, red, or I can get red, then black. Now here's the thing. We don't care about case 2 because that's not what we're interested in, right? We're only interested in 3 black cards. So if I take my red pen and I can say, okay, we're not interested in this. And also, we're not interested in this scenario. Correct? Why are we not interested in that? Because that doesn't fit what we care about. We care about all black cards. Okay, so let's reason this then. Without overthinking it, what do we expect the probability of this happening? Well, maybe we don't know, but at least this structure can give us some sort of hint. Right, so let's sort of think about this. Let's backtrack now. Let's draw this picture again, and let's imagine if we can visualize the experiment using a tree. So again, some of you may have seen this stuff before, and that's great. But the way I'm not teaching this as if I want to go through fast. I'm trying to teach this right now as if I would think about it if this were a problem that was unfamiliar to me. And I'm also going through this in a way that I want you to think about it. You know, you got to think, you know, so often, particularly in math class, you learn sort of some algorithm or some procedure and you just repeat it. You know, like, here today we're going to solve these equations. Now go home and do it for 3 hours and then come back and we'll learn something new tomorrow. But that's not what we're doing here. Here we're analyzing a problem. We want to analyze it from different perspectives, and we want to make sure that if we understand what the question is asking, that we can logically deduce the answer. So what do I mean by visualize? Well, let's start with what's happening here. Let's start with card 1. There are 2 options in this game that I'm interested in. Option 1 is that I get a black card right away, or I get a red one. Now, we can associate probabilities with both of these, correct? So we know that the probability here is 1/2, and we know the probability here is 1/2. Okay, now we want to play the game again for the second card. So there are multiple scenarios here. Here I have 2 scenarios, and here I have 2 scenarios. So the first thing is, after I get a black, I can get another black. And then, or I can get a black followed by a red. And then down here, we already told you that we're not interested in this, but we can at least write them down. Now, why do I want to write them down even though I'm not interested in them? Well, I can still deduce information about this. Knowing what I know from the first step, I say, okay, great. If I already pulled a black card, that now means there are 12 of either a club or a spade, and then 13 of the other suit. So more specifically, if I pull a black card right away, I go from 26 black cards to 25 black cards. Do we understand that? So on the next step, the probability of me pulling a black one again is no longer 26 over 52, but 25 over 52.
So you put the card back then?
I didn't put it back, no. If I put it back, it would be 26 because there would be still 26 black cards left. You sure?
I think so.
Now, okay, so the question was, did I put the card back? And no, I didn't put it back. If I put it back, then if I put the card back, then I'd be going back to having 26 black cards. Remember, how many black, you got a question?
Yeah, so why would it be 25 over 51?
That's the point. We'll see, right, okay, that's good. So that's a great question. So you asked a question and you asked the wrong question for what you meant. So instead of, if you would have said, why is the denominator 52 instead of 51, I would have said, good question. But you didn't say that. You said, did you put the card back? And no, I didn't. So what was confusing and what was the red flag for you was that the numerator seemed reasonable, but the denominator didn't, right? This is good. We're learning. Very good. So the point is that we should not have a 52 here. What this should be is this should be a 51. And I would concur completely. Because after the first step, there are no longer 52 cards. There are only 51. And in the scenario that I drew another black card, that means there were 25 out of 51 options I got. So how many options are there to go black, red? Well, then this thing has to add up to 50. It'd have to add up to 1, right? Remember, our axioms of probability tell us what? That all outcomes probability have to add up to 1. Which means this guy right here, what is black and then red? Well, this would have to be, once again, there's 51 cards left. But how many red ones are there? There's 26. And you'll notice that, and this is important to note 25 over 51 plus 26 over 51 equals 1. That's important to understand. Now, look at the first column. You have the 1/2 over 1/2. What does that add up to? 1. Remember, this was our third axiom, and I wrote it real scarily. It was very, very frightening looking last Wednesday. But what it said is that if you take all the events that are mutual, that can't happen at the same time, it's impossible for me to go black, red, and black, black. That doesn't make any sense, right? All events that are mutually exclusive, if you take their probabilities and add them up, you got to get 1. And so we can deduce that this next probability is 26 over 5, 1 in 2 ways. We can deduce it using our intuition by actually counting how many outcomes there are, or we can use the axiom. So another thing to point out is this 26. Notice that means there's 26 red cards left after the first stage, but there's only 51 total cards, which means if I'm going to pull a red one, there's 26 out of 51 chances. So I'm using classical probability, but I'm using it with respect to those axioms. All right, now similarly down here, if I go red, black, what's the probability here? Here is going to be a 51 in the denominator. Here's a 51 in the denominator. Now it's just going to be flip-flopped. Here it's 26, and here it's 25.
So say you're playing like a game with this, and so the first option you have is the half, or half and half. So, okay, so you pick the black card first, and then someone said you want to push the black and go further and see if you can get another black one.
Mm-hmm.
Would you go with the red one?
Well, that's up to, so that's a great, so you're asking a question on, and this is actually a famous question. I'll explain that in a second. What you're doing is you're asking what's called the, it was a famous problem. There was a show, and it's called the Monty Hall problem. And the story goes that there's a game show, and there's 3 doors, and behind 2 doors is a goat, and behind the other door is a car. And if you know where one of the goats is, effectively, do you risk choosing, what's the probability that your guess for the car is correct? So we'll talk about that soon enough, but that is called what we call conditional probability. So the question that was asked was, if my first card is black, what's more likely to happen for my next card? And the answer is you're more likely to get a red one. It's close, but you're more likely to get a red one. Because there's one more red card in the deck at that point than there is a black one. Now, what's nice about this sort of tree that we're drawing is there's symmetry. Now, I didn't draw it necessarily symmetric, but you see the symmetry, number-wise at least. And if I had more space, I would make it look visually more symmetric. Okay, so we can do this thing again. That's a good question. And if you're interested in that, we'll talk about it soon enough, but it's called conditional probability. Given that you know some piece of information, what is the probability about something happening? Okay, so we can play the game again. I'm not going to draw this out, but imagine this guy has 3 scenarios now. Excuse me, not 3 scenarios, 2 scenarios. So there's 2 scenarios at the 3rd stage. And then this guy has 2 scenarios. And then this guy has 2 scenarios, and then this guy has 2 scenarios. And what is this scenario? The scenario is it's 3 black cards, and then there's a scenario where it's not. It's black, black, red. And then down here, we don't care about any of these because these guys are not in the scenario I'm interested in. Now, I could write them out, but it's redundant at this point. So what is the probabilities of this scenario happening? Well, hopefully you guys are able to reason that now there is only 50 cards left in the deck. And since there originally were 26 black cards, but I've already taken 2 out, I'm down to 24. Black cards left. Does anybody have a question about that? By the way, here's another cool thing that I should have pointed out. I did on the previous page. But instead of me writing 1/2 here, what's another way to write the number 1/2, more descriptive of what's happening here? Well, another way would be 26 over 52, or 26 over 52. And for full sort of clarity, this guy, there's still 26 red cards left, so 26 out of the 50 cards are red, so that would give you 26 over 50 of that probability. Okay, so now the question is what to make of this table. We didn't have to draw out or write out every element, or excuse me, every outcome in the sample space. What we did is we looked at it differently. We said, let's look at how the scenarios of how the game can be played, or more, I guess more correctly, how the experiment can be played. And all I'm looking at is the branch of my tree that has the information that the question asked. At least the first part of the question. Again, and for those of you who don't have the homework in front of you, problem 6A says, what is the probability that you draw 3 cards and all 3 of them are black? And we're trying to answer that. Does anybody have a question at this point or a comment? Yeah.
26, is that because there's a higher chance that it's like you get a red and a black card than getting a red and a red card?
Are you talking about the 26 here?
The 26,
or here?
26, I guess.
Because there's 2.
There's
Okay,
like
so here, that's actually a good question. So let's go back to the far left here. I want to make sure we're all on the same page. So you want to think of the first sort of column is this. You want to think of this column as card 1. So you want to sort of visualize this experiment as follows. So card 1 is sort of this column. And then we're going to play the game again. This is what happens for card 2. And then this third column is going to be card 3. So if we go back to the first column, card 1, here's what we have. We have 52 cards in a deck. There's 50. If I'm going to pick one card, I have 52 options. Now, 26 of those cards happen to be red. 26 of those cards happen to be black. Which means if I am going to randomly pick one, there's 26 times it'll be black, and there's 26 times it could be red. So that is where I'm getting the 26 over 52. Now, it just so happens that 26 over 52 is 1/2, as our intuition tells us. If half the cards are red and half are black, we would imagine that the odds of pulling a black one would be half. They're equally likely. Does that make sense?
I guess I'm asking, like, why is the numerator in that one's going decreasing and the other one it's the denominator?
Well, it depends. Each scenario is going to matter. So if we're talking about the numerators, if you go from card 1 to card 2, here's the thing. There are now only 51 total cards. So that's why the denominator decreases by 1. Because instead of having 52 cards to choose from, you only have 51 to choose from. Now, why does the numerator change? Well, it only changes in this scenario. It doesn't change in this scenario. Let's see why. In this scenario, we've already chosen a black card, which means if we are to choose another black card, we don't have 26 options anymore because one's already sitting on the other side of the table. I now only have 25 options for that black card. However, if I happen to choose the red card, there were 26 ways I could have done that. So that's why that numerator is still 26. So the fact is, this number 26 is staying the same from here to here because I didn't pull a red. I only pulled a black. There's one less black, same red. Now down here, it's the opposite. If I pull a red first, then there's still 26 black cards left. But if I pull a red first, there's only 25 red cards left. Now at the third stage, since I've already pulled 2 cards, there are only 50 cards total. And depending on what scenario I am, there's either 24 black cards or there are 26 red cards. Now, this might help sort of help with the confusion. In this scenario, in the scenario where I go black, red, say black, or the scenario where I go black, red, red. So notice where I'm getting these from. This B and R are already guaranteed because I have a B and then I have an R. And then at the third stage, it can either be BRB or BRR. Yeah.
Like if it keeps going on like this, so there's going to be no more reds on the bottom, and there's going to be no more blacks on the top.
If you kept going, yes, yeah.
But you would have all the other color on the other one.
Right, right. So another way to think about it, yeah. So another way to think about it, what's happening here? Well, here there's 50 cards. Well, let me change. In these two scenarios, here there's 50 cards. Now, if I'm going to pull black and then red, that means that there's 25 blacks left. There's 25 reds left. So if I pull black again, what am I left with? Well, that means this guy has to be. Again, so let's remind ourselves. Both of these guys, there's 50 cards left. So both of these have denominators of 50. Now we have to ask ourselves, what are the total options? So if I'm going to get a black on the third card, there's one black that's already gone. So instead of having 26 options for black, I have 25 options for black. So this would be 25. And then same thing down here. If I'm going to get black, red, then red, well, if I've already pulled one red out and I've already pulled one black out, then there's 25 of each. So I would say that this is 25 over 50. So notice that if you think about the columns, everybody in this third column will have a denominator of 50, but the numerators will be different. But there's symmetry all around. It's not hard to fill in these probabilities if you wanted to. But at this point, they're redundant. We don't need to fill in anything at the bottom because the only scenario we are interested in is this. This is the only guy we care about. All the other guys, well, for this particular problem, we're not interested in. Right? We were asked to find what is the probability you get 3 black cards. Does anybody else have a question? I don't know if I made that more clear or unclear. If there's something that you guys want me to clarify, please ask. These trees turn out to be very useful because and you could have done trees with the coin toss stuff too. But the reason we chose not to draw a tree with the coin toss is because it was easy enough for us to visualize a sample space. Because if I flip a coin, say 3 times, the sample space is only 8 elements. The sample space for this is massive. So what I'm doing is I'm sort of only looking at the important parts of the sample space, or at least I shouldn't say the important parts, the parts that are of interest to me for this particular problem. Now, if we trust that this table's correct, how do we get the actual answer from this? Because all I found were probabilities at each step. This doesn't, at least, it doesn't explicitly say what's the probability of getting 3 black cards. All this number tells me right here, this number tells me if I already have 2 black cards, getting a third is this. That's all this number tells me. It doesn't tell me how to get all the way there. So we need to come up with a way, or at least use our axioms of probability to figure out how can this table be of use to us. So that's the next step. Once we visualize it this way, the next step is what to do with it.
So then from there, that's when you take the 26 over 52 times the 25 over 51 times the 24 over 50.
So you want to multiply them together, right? That's fine, and that turns out to be correct. But the question I would ask you is why? Why is it correct to multiply them together?
Trying to overall the probability of getting that sequence, right?
Right, but I mean, just because it seems intuitive, though, why is it logically sound? See, that's the question. So it was pointed out that one way you could think about the probability of BBB is to multiply this, this, and this. And that turns out to be the correct thing to do, but the question is why is that correct? Why do we multiply them together? So let's state it like that.
Isn't it because you're looking at all the possible outcomes that could possibly happen, so you're trying to calculate like how many outcomes it possibly is, and what are the chances of you getting the 3 black cards in a row?
Okay, so you're hitting some keywords. The keywords are, well, you said possible outcomes, but how do we know that? We didn't list them all. How do we know that these are the possible outcomes? So, and I'm not saying you're wrong, but what we need to do is we need to figure out how our axioms of probability give us a way to quantify this probability using this table. And you're right. You're right now the same way, Philip, you said 2-3 weeks ago now about how we quantify. You take total number and you divide it into something, right? And we saw that that's the definition of classical probability, but that only works if we know the total numbers of things. And we don't know the total number of things necessarily. We have to be a little more sort of curious, or a little more creative with our axioms. So what we need to do is we need to somehow, we need to say, okay, O'Grady made us write these 3 scary axioms down. And I want to know how I can use these things to figure out what the probability of getting 3 black cards in a row is. And the cool thing about this is, look, I could come in here and just say, here's probability roll, blah, do this. See, I don't think there's any learning happening there. That's just me giving you some abstract formula, and then you're supposed to trust that it works. Now, of course, you might argue that everything I have on this board is abstract to you and you're confused. And I apologize if you're confused, but I would remind you to remind yourself that, yes, this is confusing the first time you learn. It takes some critical thinking on your part to make sense of this. And if you put enough time into it, eventually you will. And then once you realize how I constructed it, once you get that far, then hopefully you'll realize that then now there's a bigger question in purple. Okay, now I understand how this little tree was made, but what is it telling me? So here's what we need to think about before we do something. We had some words last class, mutually exclusive. We talked about this thing, two things that can't happen at the same time. We talked about how those probabilities behave. What can we do? Well, one of the things that we can, at least, and this goes back to your question or comment at least, one thing that our intuition tells us is that what happens in the second card is going to affect what happens with the third card, right? And what happens with the first card affects what happens on the second card. Do we all understand that? So another way, you could see it in numbers, or you can just use your intuition. If I get a black card first, that affects how likely I am to get a black card the second time. So what we're saying is everything that happens in column 2 depends on what happened in column 1. Do we understand that? Everything that happens in column 2 depends on what happens in column 1. And more is true. Everything that happens in column 3 is dependent on two things. First, it depends on what happened here, but also depends on what happens here. So let's make sense of this before we show you how to solve the problem. So if we just use sort of English, the likelihood, maybe that's a bad word to use. So the tree shows that the probability of, say, getting 2 blacks in a row depends on let me write it a different way, because that might seem sort of obviously that we shouldn't. So the tree shows the probability, let me write it like this, of a black on the second card. And the key word is here, depends on what card we got first. So more specifically, the probability that I go black and then black is equal to something, and the probability that I went red first and then black is equal to something else. So the probability that I went black and then black we go back to the tree, and this is something that's also very confusing. The probability that I go black, black is going to depend on what happens at first, right? What's the probability I go black, black if I get a red card first? Give you a hint. It can't happen. 0, right? So let me explain that again. So the probability that I go black, black equals 0 if first card is red. Now, what's the probability that I go red, black? Well, the probability that I go red, black is not 0 if the first card is red. If the first card is red, then it is possible that I get a black card on the next one. Now, that tree doesn't tell me what that is right away, does it? So here's where students will get confused. This probability, this 26/51, does not tell me, it does not tell me the probability that I go red, black. All this tells me is the probability that I get black after getting red first. So there is a subtlety there. Let me repeat this. This number right here, 26/51, it is the probability that I get a black card second after I got a red card first. So how do we make amends with this? Let's go back here and say this equals what? Well, again, 26/51 equals the probability first, excuse me. I have to say this very carefully. So in English, this is the probability the second card is black given first is red. So that's different than asking what's the probability I go red, black. Yeah.
Why isn't the probability 1 to 4? Like, because you have to get the red card first and then the black card, but you have to have it in that order. And it's like a 1 to 4 chance of a deal like that.
Well, why would you have a 1 in 4 chance?
Because you either get, I guess, like, actually even more than that.
No, you wouldn't, right? Because that's what we're trying to deduce. We're trying to deduce what the probability is. So all we can say right now, all that tree showed us is what's the probability something happens given something else. So we're in sort of inventing this sort of new terminology, this idea that one thing depends on something else. That's what we're saying. We're saying that getting a black card on the second card depends on what happens with the first card. Because we know there's a difference. If I got a red card first, then getting a black card on the second one is not going to be the same likelihood as if I get black, black. I mean, that's what the tree's telling us. So getting a black card here is different than getting a black card here. Why? Well, here there's one black card missing. So for me to get it 2 black in a row, that's 1 less black card for me to use. Same thing down, excuse me, the opposite down here. If I've gotten a red to begin with, then there's still 26 black cards left. That's what this is telling me. So we have to figure out how to determine this probability given these 3 things. Now, of course, you already either guessed or knew the right answer, and that's to multiply them together. But what I'm asking you to try to understand is why. Again, what do the books do? The books come in and say, here's a formula, use it. They don't tell you why it's true. They just tell you to use it. I don't want to do that. Right? I want you to understand why. So anyhow, before we go, because I know we're out of time, so what this means is this means the following. So, and we're gonna go. We'll finish this on Wednesday, but here's what we're gonna do. So, we use the notation probability of A/B to mean the probability A occurs given B did. So this B is not meaning black card. This just means 2 different events. So what do we think the probability should be? Well, it turns out, and I'll let you think about this and then we'll leave. So it turns out the probability of A and B. So 2 things occurring. That is always going to be equal to the probability of A times the probability of B given A. So, and this is true for any events A and B. Now, let's apply this to our problem. So the probability of, say, black and then black would be equal to the probability that I get a black on the second one times the probability I get a black given I got a black in our example. So it's going to take some thought from your perspective on this, and we're going to come back to this on Wednesday, and we're going to really explain. Well, I'm going to attempt to. I don't know. Hopefully it works. What I'd really like you guys to understand is, why is this the case? Why? And by the way, the reason it's why can be seen in the tree, but it has to be deduced from the axioms. Anyhow, guys, thank you. Hopefully you're not too confused. That wasn't the plan. Hopefully you're more intrigued. I would rather you do that than anything. Have yourselves a good day. I appreciate it. Thank you very much. And we'll finish this later.